Hello, a nice welcome to today's class. We are going to be covering calculus, third installment of the mathematics of machine learning and AI. So, as a motivation, I'm going to give a quote or a simple passage in Hawking's book, A Brief History of Time, and it's going to more or less help us appreciate how wide and diverse human knowledge really is, and more so mathematics. Hawking describes how it was very easy for a person to sort of know everything that was there to know in a certain discipline, mathematics, calculus, physics, and that was no longer the case as more people were coming up with ideas, and those ideas were being tested and others were being discarded, and in some way sort of had to acquaint yourself with the most recent discoveries and to know what is really up to date in your current domain. To further complicate the issue is that branches or new ideas were being discovered. So essentially, when you get out of school, you have to keep learning. As it's hilarious, it's funny really, because you can be studying something at the university back then, and even before you are really done with the exam, the knowledge is sort of outdated, or some of the theories have been discarded. So it helps us to really appreciate how diverse and dynamic knowledge is evolving over time, considering that Newton himself died in the 1720s. We can see a very large gap of around 300 years. So you can really imagine how big the field of calculus is. So it is more than 300 years old, and it's really hard to sort of memorize everything that is there to learn. I would really encourage you to avoid regurgitation or sort of memorizing everything that you come across. Calculus is a very wide branch. You can view your brain as a catalog or a repository that you can store the general outline of the ideas, and not per se the most intricate details of formulas, as you can easily retrieve them from a search engine or from a chatbot. So that is really the high level view of calculus that I wanted to focus on in this introductory part. I'm going to focus on derivatives and antiderivatives. And again, in this series, we are going to continue using Python examples as well as mathematical notations, and giving a background of how you can use the concepts that we learn to build something. Calculus is a branch of mathematics that deals with the study of the rates of change and accumulation of quantities. So, borrowing from Newton's view of calculus, it is more about the study of motion and how bodies evolve over time, or how they react to different forces. And that is what calculus is in a nutshell. Then we can go to the idea of a function. The idea of a function goes hand in hand with what we studied in our first lecture. In our first lecture, we introduced the idea of operators and notations. So a function is a rule that assigns each element in a set, i.e. the domain, to exactly one element in another set, that is the range. So the idea of functions can be extended into programming and programming languages. In particular, we are going to be looking at functions in Python. So a function in general comprises of a function name, which can be optional at times, the parameters, and the operation which is to be performed. About the operation, a function can be void. It doesn't return anything, or it can return a value. So in there I have some examples, and in that code I have a lambda function, and then a declarative function, and then an example of how a good function looks like. A lambda function is really a function that is short and pithy, i.e. and most of the time it consists of one lines. So you can see there the function is adding two parameters a and b, and it's returning their sum. So then there is the declarative way. So in this case we use the keyword def, and then we define the name and the parameters, and then a return method if it's there. And then we have an example, or say two examples there. One uses the declarative approach and another the lambda approach. And to mention something, in Python we have some very nice functions. That one approach that you can use is to assign values in the parameters. Say you can give a threshold value. The good part is that you can omit the threshold part. If you want to find the sum, you can pass in a list and a threshold, or you can just pass in a list and it computes the sum for you. And I can touch on a small bit about TensorFlow. So TensorFlow has a class that you can use in conjunction with your custom methods and be able to do operations that you require. So what are the different types of functions in mathematics? So we have a polynomial function there. So f of x is equals to some values. The polynomial functions mostly deal with finding roots and the properties of those roots. Then there we have some trigonometric functions like sine, cosine, tangents. This kind of functions are repetitive, so you can use them in areas that require a repetitive kind of approach. Then we have exponential and logarithmic functions. So there we have a function f of x is equals to e to power x, and then a natural logarithm there. So what is a derivative? A derivative, f of x, is denoted by f prime, or f with an apostrophe there, or d of f over d of x. So there is the function that you are differentiating and what you are differentiating with respect to. So you are differentiating f with respect to x. The derivative of a function represents the rate of change of the function with respect to its independent variable. So there we have some rules of differentiation. We have the power rule, and then we have a product rule and a chain rule there. So essentially these rules are used to determine which approach you are going to use to differentiate a function, and so these rules are very essential when you want to get the derivatives of a function, especially when the function is composed of two or more types of a function, or of a function and other composite functions that are not easy to differentiate. The current climate, there are some good libraries out there that you can use to differentiate functions without necessarily having to write your own code. And look at integrals. So the integral really is a function that gets the area of a curve. So it's an operation that is used to get the area of a curve, or in a more professional definition, an integral represents the accumulation of quantities, and it is the reverse of the process of differentiation. So we shall be using integrals in statistics, especially when you're going to be doing PDFs and CDFs, and by extension finding the expectation and mean of values. So we shall cover this in great detail in another lesson. So there we have a definition of a definite integral of an interval and how you denote it. Also there we have the fundamental theorem of calculus, and it essentially defines the relationship between differentiation and integration. What I can really drive home today is that your emphasis should be knowing as many functions as possible and their properties, and this can go a long way in assisting you to do problem solving exercises. In general, you can become a better machine learning programmer by knowing as many functions as possible. So one of the important functions that we have in machine learning is the sigmoid function, and we have a notation of the sigmoid function given there: 1 over 1 plus e to power negative x. This function essentially does, it sort of compresses the input value to a figure between 0 and 1, and it works well with the probabilities, as we expect probabilities to be a value between 0 and 1. Some of the applications that we can use sigmoid functions is in classification problems, where you are trying to figure out whether a statement or a phenomena is true or false, 0 or 1. So there I have a Jupyter notebook, and inside it I have some code. Code deals with the usage of a sigmoid function. So we declare the sigmoid function using a lambda. We also define another predict function that takes in x and the weights, and then we are doing the squashing. So we pass in a matrix or an array and some weights. So in our predicted probabilities, we have all values being between 0 and 1, and that is what a sigmoid function essentially does. So another term you shall be hearing very often is the term activation function, and an activation function is a switch in a more layman kind of definition. So an activation function assists the neural network to learn the complex and diverse features of your data, and in that way you can improve it. And then we can go back to trigonometric functions. Again, trigonometric functions are used to describe periodic behavior like signals and wave functions. And one revolutionary concept is called Fourier analysis. In this process, we try to decompose a wave into its constituent functions. We can find that a wave is composed of maybe several sine waves of different frequencies, and in essence we are trying to reduce it into smaller and easily manageable functions. The trigonometric functions is activation functions. So there we define an hyperbolic function there. So the hyperbolic tangent is defined by that function there, f of x is equals to some exponentials. So this one essentially has a different range from -1 to 1, and this can work with normalizing data and activation functions also. And then there is another function called ReLU, or rectified linear unit. So ReLU is defined by f of x is equals to the maximum value between 0 and x. Again, it is used as an activation function. ReLU can be used in LSTMs as an activation function that assists the recurrent neural network to mitigate the issue of gradients. At times, you can find that the gradients explode or they vanish, and by using ReLU and other similar activation functions, you can avoid this issue. There we have a softmax function. This works like the sigmoid function, only that we are using it in a broad spectrum, where you can use it to do multi-category classification. And then another important function is the exponential function. The exponential function essentially is used to model growth and doing time series analysis. So there we have a nice equation that shows the rate of decay. So f of t is equals to f naught multiplied by another exponential function there. And one area we use decay or exponential growth is in defining learning rates. So there we have a learning rate equation. So the learning rate equation is equals to the initial learning rate times a decay factor, which is raised to the number of epochs over the decay steps. So the learning rate is a fundamental concept in deep learning and is normally done experimentally. So you try to experiment as many learning rates as possible, and you see which one works for you. Scenario, most frameworks will provide for you some inbuilt functions that you can use to regulate learning rates. Then there you have a logarithmic function. So we can use the logarithmic function to do scalings and again to do logistic regression. Logarithmic functions are helpful in finding MLE, or the maximum likelihood estimator. We shall be looking at MLE in our statistics class, and we shall see that it is also a very crucial concept in machine learning, or in predictions generally. So there we have a step function and an identity function. The step function is being used to group items depending on the value of x. So there we have an identity function, f of x is equals to x. So the idea of an identity is to maintain a property. So again, we can have piecewise linear functions. This can consist of several linear functions. So these are particularly helpful in doing approximations and in classification and regression problems. So let's look at the broad applications of calculus, and I'm going to cover this section with respect to neural networks, as we shall see in our class on this topic. And one of them is in an algorithm called backpropagation, and backpropagation is an integral part of layers. So backpropagation is the algorithm that we use to form associations between layers. It uses a chain rule to find the derivatives of certain functions which happen to be composite, or those that happen to have several functions within them. So again, we have integration. Integration, we use it in statistics to find expectation and the idea of moments. Other than backpropagation, we use calculus in other optimization problems, and this goes hand in hand with another great concept called gradient descent. So we use calculus in other optimization algorithms like gradient descent and stochastic gradient descent to optimize the loss function, or to really assist our neural network to reduce the number of errors. So the idea of gradient descent is to deal with the problem of local minima and local maxima. So we can view our grand problem as one big mountain, and that mountain is composed of smaller mountains, and we are trying to find the lowest point. So in our mountain we have some lower points, or yes, we have some lower points in our sort of mini mountains in our larger mountain, and the idea of gradient descent is employed here to refine the machine learning algorithm. So again, we use calculus in errors and cost functions. So by errors, we are trying to compare our predicted values versus our actual values. Calculus can be used in penalization and regularization. So at times we find that some of our weights can be bigger than others, and this can produce erratic learning rates and incorrect values in our predicted figures. So by penalizing some weights, we are sort of reducing the influence of one particular feature to be more representative of the data as a whole. And then there we have SVMs. We shall cover this in we shall cover SVMs and other algorithms in our class, which will cover supervised versus unsupervised machine learning, and we shall get to see what support vector machines are. And again, if you can remember, in our last class we did a PC analysis. Calculus is also used in eigenvalue decomposition to identify the principal components in our data. And then calculus is also used in kernel functions. So the kernel operations simply involve kernel methods involve solving the equation ax is equals to 0 for a matrix A and a vector x. So again, kernel methods are very essential in PC analysis, SVMs, and other nonlinear problems that we might have in our machine learning algorithm. And to really reinforce what we said in the beginning of this lesson, that calculus is a very broad category. We have concepts like discontinuity, differentiability. Another really branch of calculus on its own is partial derivatives and differential equations in general, and these are very helpful in physics and applied mathematics. We have calculus extended to the complex plane, i.e. over imaginary fields. So thank you very much for staying in to the end of this lesson. In our next class, we shall be covering statistics and probabilities, and we are going to sort of be building on top of what we have been learning about matrices and calculus and operations. So thank you very much, and tune in to our next one.